So, good lunch. Can see a bunch of people taking a nap at the back. Yeah, good lunch. Okay, so grab a bottle of water, wake up. Your next speaker is an interesting person. Please meet Gaurav. Gaurav is a consultant, dev, trainer, runs his own firm based out of Chennai. He helps organize Chennai Go Meetup, the Go India, Golang India remote study group. Um, he has a pretty eclectic background in terms of other things he does. He reads a lot, he treks, and he programs in 12 languages and spent 14 days last year trekking across 5 states in the Northeast. So that's your next speaker. Over to you.
Hello. Good evening, everyone. I hope you had a good lunch. Awesome. So that's my talk today. An investigative walkthrough of Go's channels. Alternatively, it was titled as Learning About Go's channels, but that was boring. So my name is Gaurav Agarwal. That's the agenda for today. Audience poll, program walkthrough, a simple scraper which I had written earlier to demo Go's concurrency to a lot of people. So I'll be deep diving into Go's channels internals. Many of you might not be familiar with what goes on under the hood, and this talk is basically intended to do that. If demo gods permit, I'll have demo and questions. I'll take questions during the demo. So that's it. All right, let's get started. So that's me. I'm a software engineer and product developer. I run my own small consulting agency called Agarwal Consulting. I'm ex-Tarka Labs, ex-BrowserStack, ex-ThoughtWorks. I'm also the co-organizer of Chennai Go Meetup. I also help in running the Chennai Go remote study group. So it's on the first and third Thursday of every month. 8:30 to 9:30 p.m. You can join remotely. So these are the links to it. I think Dinesh talked about it before that. Yep. Awesome. So the upcoming meetup is on Thursday, 24 January. Yeah, that's a slide which I was talking about. All right. So how many of you are students or are new to programming in Go? 1, 2, 3, 4, 5. Okay, awesome. And how many of you are familiar or have worked with Go's concurrency? Pretty much rest of the crowd, right? Awesome. So I'll walk you through a simple scraper algorithm first for this talk, just to set context. So this scraper is like, it scrapes for a particular type of products from Amazon's product listing page. So I'm looking at various TVs, MI, BPL, all those. And basically what I want is a struct which has the name, the link, image, price, and the reviews for each of the products on that page. So for each product, I get, I'm basically using this library called Soup. It's a port of beautiful soup, which is in Python. So so I'm just iterating through each of the DOM element and picking all the content which I need. So in the first iteration, I get the link, name, image, and price. In the second iteration, for the reviews, I have to visit the product page and then get the reviews. So for each review in a product page, I get its name, rating, and content. So tying it all together, I just call the parse product function, which gets the reviews for that product and just encodes it out to std out. So this is the output which you'll be seeing, which you should be seeing once the program runs properly. So tying it all together concurrently using Go routines and channels. So just to make this entire code run concurrently, I add 2 things. One is the Go keyword, and I read from a channel. So while I'm writing, okay, I'm receiving from a channel and I'm sending to a channel. So deep diving into Ghost channels. So before that, I'll just show the output, what it currently looks like by running it. So I'm just, so this is live. This is not a recording or anything. So it takes about 7 seconds to get data for 24 products. Not bad, I guess. Um, so, so Go has two kinds of channels, as we all know. Like there's the buffer channel and there's the unbuffered channel. The buffer channel takes in the second argument, which is the size of the channel, and the unbuffered channel does not take any arguments. Basically, if you don't pass any arguments, it becomes an unbuffered channel. So to send to a channel, you pipe into the channel. So you put an arrow into the channel, and if you're receiving from a channel, you put an arrow which is coming out of that channel. Um, so I'm adding breakpoints in my code so that I could show you that demo. So once I put that um, breakpoints, I get this. So PCH is my make-chan product of make-chan product, basically, my product channel. And this is the properties of it, which I see, which I can inspect in my debugger. So it contains a lot of attributes. You have queue count, data queue size, buff, LM size, close, LM type, send, receive queue, send queue, lock. That's a mouthful. All these attributes, they come from the HChan struct, which is Go's internal implementation of channel, which is what all of the channels are copied from, are instances of. So the attributes of the HChan struct, they can be broadly classified into 4 groups: the type information, the buffers and queues, the counters, and locks and flags. So let's look at each of the groups. I think I'm rushing too fast. Probably I'll slow down. The type information. You have LM size, the first attribute, which represents the size of a single element in memory in bytes. So if you had been paying attention to Maya's talk, she was talking about the stack and the heap, right? So LM size represents the size of an element on the stack. It does not deal with the heap as such. It just shows how, it just notes how much memory this particular element, in this case, my product struct, in memory, in a stack. The LM type information, so product takes 88 bytes, string takes 16 bytes, and an array of struct takes 24 bytes. So it adds up to 88. You could check the math on that. And int takes 8 bytes, similarly. Whereas LM type is a lot more detailed information about the element. It also contains like the pointer information of where exactly this element is. So it contains the runtime information of that element as such. Used when message. So basically, this is used when we are sending and receiving from a channel, right? We copy over messages. So Golang works on the principle of do not communicate by sharing memory. Instead, communicate. Sorry, I keep forgetting that one. Communicate by sharing memory. Okay. So this is okay. So the next few slides are going to talk about the buffer channel implementation. So this is what a buffer channel is, like a product of 3. So a buffer channel obviously contains a buffer. So what's the difference between make channel product of 1 and why is it different from an unbuffered channel, right? Buffer size of 1 should be equal, it should be similar to unbuffered channel, but it's not, because you have a buffer in case of buffer channel, which is nothing but a circular queue. So the data queue size is determined by the parameter which you pass in, the second parameter, second argument which you pass into it. And the buffer, so this is what a buffer would look like. So that each slot takes in a product, basically. You have this receive queue and send queue, apart from this. So pseudo G. So pseudo G is a special structure. So each of receive queue and send queue are instances of pseudo G, which are nothing but Go routines. It literally represents the running Go routine information. So it contains the Go routine, a pointer to the Go routine. Is it selected next previous? So it's kind of like a doubly linked list implementation. I hope this is quite visible. All right, so you have the first and the last. So I'll go back. You have the next and previous, right? So in that, it shows first and last. So it's a doubly linked list which contains all the Go routines which are receiving or which are going to be. So I'll take the receive queue example first. So all of the Go routines which are supposed to receive from this channel would be enqueued onto this receive queue, would be added onto this receive queue. So they'll be linked. So the first one would be null, the first pointer. The receive queue, the last, they would just keep on attaching themselves. So I'll come back to why this is important. Before that, I'll first cover the counters which the buffer uses. So we have already seen the data queue size. Data queue size is basically how many elements this particular buffer channel can take. The queue count is what is the current capacity which has been used of the channel. So if the data queue size and queue count become equal, the buffer channel would block on sending. Apart from this, you have sendx and receivex. So the buffer channel, so this is an alternate representation of the buffer channel. You have the buffer, sendx, receivex indexes. So these are basically indexes for the circular queue. So let's just go through the scenarios first. So you have an empty buffer. You are performing an enqueue operation on it. So the sendx and receivex, so the sendx gets updated. So the next insert into the circular buffer, circular queue, will happen on the first index, first slot, basically. The 0th slot is already full. The receivex, on the other hand, would happen still on the 0th slot because that's the one which is filled. We'll just go through, we'll add 2 more, and then the sendx receivex becomes 0, queue count and data queue size become 3. They become equal now. Since they are equal, the buffer channel would block on any further sends. A receive. A DQ is nothing but a receive operation on the channel. And that's when the sendx becomes 0, receivex becomes 1. So the next read or the next receive from the channel would happen on the first slot. Make sense? Awesome. So, okay. So this is the last slide before I get to the demo, last set of slides. So you have the flag which marks the channel as closed. What happens when a channel is marked as closed and you try to receive from it? You get 0 values, right? You get 0 values and you get a error flag as true. So you can mark a channel as closed from any of the Go routines which are reading or sending, which are receiving or sending to it. And apart from this, you have a lock. Okay, so channels are thread safe or are Go routine safe, right? You still need a mechanism for or a semaphore to ensure that all of these Go routines can they do not have a race condition. Like 2 Go routines are not reading and writing into the or sending and receiving onto the channel at the same time. And if that happens, bad things shouldn't happen. It should probably be Go routine safe. So this lock, it's a mutex which controls access to the channel, basically. Okay, awesome. Okay. That's the boring stuff. Hopefully, this would be like cool. So watching channels in action. So I'll be taking questions during the demo. Feel free to raise your hand and ask questions. So this is my code, the concurrent scraper code which I was talking about earlier, which I was showing you earlier. So I'm receiving, so the pass product sends to the channel, which is my PCH, which is what I'm passing to it, and my main function receives from my PCH channel, which is my product channel. I've put breakpoints on it. Let me make the channel as buffered first, because that makes for better demonstration. All right. So it first tries to receive from the channel. There's nothing to receive on. So this is a make or break demo. It kind of like depends on what Go routine gets executed first. So I don't know. Okay. So I have already so I'm so I tried receiving from the channels first, and so my receive queue becomes filled up with one Go routine, which is my main Go routine, main dot product, and my data queue size is 3 as usual. Now I'm trying to write into my channel, and it just becomes null because it takes from the receive queue. It does not actually enqueue anything into my PCH into my buffer. So, oh yeah, I'll probably add. I hope this is visible. Awesome. So I'll remove this one. So I'm just reading from the buffer. One last expression, PCH dot buff of 2. That's it. So these are empty products, zero value products, basically. Um, so for a buffer channel, the buffer gets allocated into the heap. The entire the number of slots, the capacity of the buffer is allocated completely onto the memory. One thing to note. I'm still receiving and sending to the channel. Now, if you see, my sendix and receivex gets updated. So it's at 1, 1 each. The queue count is 0, so there's no element which has been pushed into my buffer yet. It's still 0, 1. Okay. So there is something which is trying to receive from the channel, but we haven't gotten lucky as to 2 sends happening at the same time before receives happen. So let me run a few more iterations of it. So if you see now, my queue count is 1. My sendx and receivex has become like 2 and 1 now. So my next receive is going to happen on slot 1. So this is where my data would be, on slot 1. My sendx, the next write would happen on this buffer. The read happened, the write happened. So now the second one is filled up. So I'm just trying to see if I can get a send queue filled up instead of like just receive queue. So by the way, I'm using the Delve debugger. This is Visual Studio Code. Right, third time lucky, I guess. I could cheat over here, actually. What's the syntax for sleep and go? Time.sleep. So I'm going to stop my receives from happening. I'm going to make my main sleep for 1 second. Till that time, I'm hoping that more sends happen to it. Yeah. Yep. Okay. So sends are happening. So you could see that a send has happened on the buffer before receive is happening. So 1, 2, 3. my queue is filled up. So basically, like now I have more than so I have 4 entries written into my, so I have all my slots on the buffer are filled up. All the 3 slots are filled up. And now whatever enqueue is happening into the send queue is basically blocked Go routines which are trying to write, which are trying to send to the channel. Make sense? Awesome. So this was it. So this was for buffer channels. Let me look at what happens with unbuffered channel. So I just made it unbuffered now, just by removing the second parameter. It runs, but I don't get any output for these 3 expressions because there's no buffer, basically, no buffer allotted. So it's a pointer, so it's null, basically. And my queue count is 0, and also my data queue size is 0. It's not 1, it's 0. There's no buffer which is being used at all with the unbuffered channel. Um, Everything is stored within the send queue and receive queue. So now I'm trying to send something onto the buffer. The first send would block until a receive happens in a unbuffered channel. And where's my element then, right? Where's the information which I need to send from one Go routine onto the other? That's within the pseudo G struct, which has an element and which contains my product. So, so my receive queue would probably not get full. I'll probably remove this sleep now. Hopefully, not a lot of people are sleeping after lunch. Okay, it's taking a while to run. So more about Go routines, right? So the way the Go scheduler goes, so the difference between threads and Go routines is that threads are at a kernel space level, whereas Go routines are at a user space level. So whenever you run Go commands, they are generally mapped ms to n, like whatever uh, Go routines, how many ever Go routines you create, they generally take up like 8 bytes of space, and like the stack of a Go routine takes like 8 bytes, and all of those Go routines are mapped onto n threads on the so m Go routines are mapped onto n user space threads, kernel space threads. Sorry. That's it. So my receive queue is getting filled up now. So I'm ready to receive an element on this, which is empty basically. So when the next the next send happens, it basically shortcuts and writes directly or sends directly onto the first element of the receive queue. So it maintains the queue um, structure, and that's what I had to show for the demo. Any questions during the demo? No? Okay. So summarizing channels. So channels are first in, first out because of the receive queue, send queue semantics, buffer channels, and also even the unbuffered channels use receive queue, send queue. So do not communicate by sharing memory. Instead, share memory by communicating. That was the thing which I forgot earlier. So channels are Go routine safe. You can use them across as many channels as many Go routines as you want, and they are first class citizens basically. So channels and message boxes in Erlang come from the same paper, the communicating sequential processes paper, and Go has made the channels, which are like the pipe which connects the processes, as first-class citizens. Whereas in Erlang, you have the process IDs, which are the first-class citizens, not the message boxes. So the references for this talk are from Kavya Joshi's GopherCon 2017 talk on understanding channels, Ankur Anand's post on diving deep into Golang channels, Gaurav, shameless plug, Go concurrency construct stock, which I had given earlier in Golang meetup. And I've used Delve debugger along with Visual Studio Code. And that's it, 40 seconds to go.
Do we have any questions? Any questions? Anyone? Okay. Thank you so much, Gaurav.